All right, let's go ahead and get started. So welcome everybody. Here we are at the end of March, and we have an interesting demo today. We've been working with Moonsense, the team there, to kind of help build out a solution which I'll let Andre introduce it, but it's a really interesting use of Decodable with a bunch of real-time feeds from devices. There's some machine learning in there. And so we're going to have Andre introduce it. Josh will talk about what he's built with Decodable, and then just a general open discussion. So with that, I hand over to Andre, the CEO at Moonsense.
Thanks, John. Thanks for organizing all of this. Nice to meet you all. To give you a bit of context, so I'm co-founder and CEO of Moonsense. We are a relatively young company doing some interesting things in the space of like unlocking first-party data for risk assessments and risk scoring. In the past year, we've been hard at work, like assembling an amazing team and shipping multiple versions of our SDK and our cloud offering with this end goal in mind of like making it easy for application owners to drop in an SDK and start collecting these like rich behavioral signals. Down to like things like the timing of individual key presses when people register for new accounts on your applications, to touches on the screen or like mouse movements, to readings from the accelerometer of the device, if this is happening on a mobile device, to device orientation and beyond. And you may be wondering why it's so interesting about this data. This data is interesting because when you take it together, it gets pretty close to like the digital equivalent of like a wet signature on a receipt, and you can use it in a number of different ways, going from like assessing device risk into supporting identity verification through a continuous authentication type of use cases. And I'm super excited about this demo with Decodable because leveraging the data that we provide through our SDK, it takes quite sophisticated stream processing infrastructure. And if you can do it through SQL, my feel is that it actually gets pretty close to like the ideal way of like solving the problem. Specifically because, you know, this SQL approach can so nicely go from like processing a stream to then allowing you to backfill a feature store for model training purposes based on historical data, and all can be more or less the same query with a little bit of like retargeting. So yeah, that's about it. Oh, and in terms of like introducing the use case we're looking at today, it's a really straightforward one. A common attack vector in certain markets when it comes to you know, bad actors is that they elderly people in particular are spoofed, are socially engineered to believe that they are talking to legit tech support centers, but they are talking to attackers that socially engineer them into installing remote access tools on their phones, and then use those remote access tools to you know, basically defraud them, either like pulling money out of their like digital wallets or bank accounts or so on. And that's that has like such a bad impact, and financial institutions, and there are so many other like players out there care about like reducing that type of fraud. So they invest in the type of models that we will play through today to detect cases where these devices are remotely controlled or the application is not truly used by a human the way you'd expect.
Great, thank you, Andre. So why don't I take over and I'll start and do a little demo. So I'm going to share my screen here. And if I get a thumbs up when folks can see it. Great. So just to sort of expand on the use case, what we're trying to do here is basically bring in the Moonsense data. And I've just got sample data for this demo. But we're going to bring in the Moonsense data, and we're specifically looking at it's the pointer data. So just on the left here, I've got a little sample payload. We can see it's, you know, fairly complex. There's lots of, you know, nested fields and things like that. So we obviously have to do a little bit of cleaning and parsing to sort of do the processing we want to do. But specifically, we're going to be looking at the pointer data. And the reason for that, and Andre tells me, is the sort of end goal is the velocity of a gesture can be derived from the pointer data, and that's indicative of whether or not this is sort of a real human user interaction or whether this is a simulated sort of bot account. So the exercise we're going to go through is bringing in, again, this is Moonsense data not cleaned up, just sort of as is. We're going to bring it into the decodable system. We're going to do some cleaning, parsing, some streaming aggregations, and we're going to finally output summary statistics on the data that can be picked up by a data science team to basically train and evaluate models. So I realize sort of I talk fast and I might not see everyone's hands. So if you have any questions, feel free to interrupt me. I won't be offended. So to dive in, we're on the Decodable UI here, and we've defined some connections. So the connection for bringing this data in is a REST source connection. So I just have a little data generator running. It's emitting basically this payload over and over again to an endpoint. We can see here the configuration. We're connected to REST. We're going to a stream, and we can see in the details pane, this is a JSON payload coming in, and we also see the endpoint. So that's the advertised sort of URL that we'd post data to for the REST ingest. There's a schema defined for this that matches very closely to the JSON payload, but I'm going to skip ahead actually to a pipeline here, which does some parsing. So we've got and a pipeline in decodable vernacular is just a running sort of process. It's SQL. And it's going to basically take the input from a stream. So we've got the stream for the raw connection, this raw POS, and it's going to output to this Moonsense parsed. And we'll take a look at sort of the schema definition here really quickly. I have gone ahead and sort of pre-populated a schema for this stream, giving it sort of field names and data types. So the next step now is actually just populating it in a pipeline. So we'll take a look and see what this sort of looks like. It is a running pipeline. We do get metrics on this. We can see sort of bytes per second, records per second in and out. And we'll look at what the SQL is doing. Let me move this over a little bit so we can see everything. So this is pretty standard data cleanup SQL. Most notably, we've got some interesting choices for timestamp types here in the raw payload. We've got like an epoch sort of milliseconds, but it's wrapped in like a string. We've got this timer here. It's got the same thing going on. And we also have in our bundle, all of our pointer data and various telemetry. They're sort of buried underneath in this object. So what we're going to do with this SQL query is basically pull these out. We're going to bring these to the top level, and we're also going to do a little bit of just sort of cleanup on it. So sort of a concrete example, we've got this wall time millis field here in the bundle client time. We're going to cut it off a little bit. We're going to pull off just the first 13 digits of it. Then we're going to cast it to a big integer, and then we're going to convert it to a timestamp. So what that does is now gives us sort of a well-formed timestamp that we can use sort of further down in our processing. And as I mentioned before, we're going to up-level some of these fields. I want to save some keystrokes. So our pointer data is sort of buried underneath this bundle. I just want to bring it up to sort of the top level of this Moonsense parsed stream. So this is a preview that's running. The pipeline is also running in the background. We're just sort of running a second one in parallel so we can see the output of this. And I'm going to make sure I'm actually sending data to it because I'm probably not. Good old live demo. So let's try that again. Okay, we're going to cancel that and we'll run it again. So once again, we're taking in the raw data through this data generator, which is now in fact posting data. For some reason it hung before. And we're waiting for results. There we go, great. So not much new and different here on our output, but what we can see is our sort of data cleanup process is starting. So we've got our wall time here. This is now a well-formed sort of timestamp that's not this epoch sort of millis. So we can start to key in on these values for our sort of downstream processing. We have a lot of nulls here. This sample data only has the pointer data, so that's just sort of ignored. And we can see here our sort of embedded fields are located and they're sort of hung up underneath there. So this is sort of a first pass data cleanup on it. But now the next step is going to be to dive into this pointer data and extract it out. Are there any questions on what I've shown so far?
Josh, do you want to explain what the preview function does?
Oh, of course. Yeah, so I forget. Not everyone uses this stuff every day. Right, so we've defined our SQL for a pipeline, and a running pipeline is just this sort of like process that runs in the background. It's highly available, fails over. It's sort of the thing that is the workhorse for data processing. But sometimes you want to see what's actually happening before you create this pipeline. So a preview is just a way that you can submit a query. It'll send it to an engine. It'll fire up a whole new execution environment, and you can sort of see the results of what's going to come out before you actually enable it. Great. So we've done a little bit of parsing, but as we know, our sort of goal here is to calculate velocity on this pointer data. So these records here are sort of embedded within arrays, and it's just sort of challenging to do a lot of operations on that, especially in sort of an SQL and a streaming context. So what we want to do here is extract that pointer data. So again, we've got a running sort of pipeline here. We're unnesting the embedded pointer objects into records. So this one's pretty straightforward. There's not a whole lot of magic going on here. Well, I think it's sort of magical, but it's pretty straightforward. So we have our Moonsense parsed data as coming in. That's our sort of from table. We're going to insert into this Moonsense pointer stream. And I'm using the term stream and table sort of interchangeably. These are streams, but of course in SQL syntax, they're sort of treated as tables. What we're doing here in the magic part is this cross join unnest. So it's this pointer data field here is an array, and this can have multiple entries within it underneath. What we want to do is actually split those entries into individual records. So it's doing sort of this self join with the pointer data, and we're giving it the label P. And every time for every entry in this pointer data, we're going to emit a new record with the top level fields here, but also the position, the DX, the DY, so the X and Y locations on screen, the radius, and the size. And if we scroll down here for our preview, we can see that we are now emitting individual records from the entries we had in this array. So we just correlate across DX27, DY208, DX207, DY208, new record on the stream, DX32, DY204, DX32, DY204. So pretty simple pipeline. All we're really doing here is sort of unnesting, or I call it demultiplexing the data from a fairly complicated input stream into individual records on their own stream for sort of further processing. Are there any questions on that?
Yeah, so the unnest of the pointer data gives you access to all of the kind of nested objects within the items in that pointer data list, like including the pressure range and.
That's right. Yeah, we could anything within the pointer data we can reference. It just gets this label P. What the sort of magic that's happening here with unnest is it's kind of like a one-to-many reflection. So we have one event coming in, which is our Moonsense parse event, but it's now emitting this sort of like many events based on the number of entries in pointer data. So for every time we get one of these events that comes in with say 5 pointer data entries, we get one event for each emitted based on what's contained. And so P is sort of like our iterator of the data within pointer data. So for this demo, we're only looking at the position data and the radius and the size, but you could access anything else that's in there. Does that answer your question?
Yes, thank you.
Great.
Hey, Josh, I think we should be able to see the effects by looking at the matrix, right? The output matrix should be like showing
yes,
like 5x of the input.
Absolutely right. Look at this. Great, great segue. So our records per second coming in it's about 1. It should be around 1. Just through rounding, we're a little under, but we can see 10 records per second being emitted. So in our sample, we've got 10 sort of pointer data entries, and that's what's happening. We've got a 10-to-1 sort of multiplier effect happening here. So far, so good? Okay, so we have pointer data being emitted. That's pretty interesting. But really the end goal here is we want to calculate velocity. So I'm gonna flip into the SQL here. Don't be too stressed out by it. There's a lot going on, but I'm going to try and make it pretty easy. So it's this really interesting sort of nested query. This could be multiple pipelines, but I wanted to sort of demonstrate us doing it all at once. And so this is the crux of what I would say the magic that's happening. And so just in this little window here, what I'm going to do is I'm going to run a preview from our command line. So I'm just echoing the inner query into our decodable pipeline preview command line, and I'm just going to parse the JSON out of it. So while that's running, we'll see what that looks like, and I'll talk about what's happening here. So we had our demultiplexed Moonsense pointer events coming in, but what we're really trying to get after is the deltas, right? We want to know what's the difference between the record that we just saw and the one previous to it. So here's a great example where you can sort of peek at the data that's come back. The magic that's happening here is this lag function. So we've established a window of the data coming in on this Moonsense pointer stream. We are partitioning it all by session ID. So all of the session IDs and these payloads are now kept sort of grouped together, and we're ordering by time. And so what lag is doing is it's saying, basically, give me the previous entry in the window for the various columns. DX is the X position. We're going to call that DX prev. DY is the Y position, DY prev, and determinate prev. And we can now see here in our preview results, here's an example. This is the regular entry, has a DX of 57, but now the DX prev is actually the previous record's value. So there's a little bit of like windowed state aggregation going on here. And that's really cool. We've basically done an enrichment, but from the same data source. And you can sort of start to piece together now, if we've got the DX and the DX prev, the DY prev, and the determinate, we can start to calculate deltas for distances and deltas for time. So I'm going to go ahead and start this preview in the background while I talk about just the rest of it. So in your mind's eye, remember, this is the data that's coming out of this inner query. Now we're going to start to calculate deltas. So the first thing we're going to do is figure out the time delta, and that one's pretty straightforward. It's the difference between the determinate and the previous determinate. So again, this is 137072. 055, and we can look back. There it is. You can do a little math and figure out what the time delta is. And sort of to bring it back to high school physics, or earlier if you were in an enrichment program, the Euclidean distance formula, we're going to take the deltas of our x-axis and square them. We're going to add that to the deltas of the y-axis and square them, and we'll square root the whole thing. And that's going to give us our total distance between these pointer events. So the last step here, any questions on that so far? Okay, so the last step, we're just going to do a little bit of extra calculation. We've figured out T delta, we know our D delta. If we've got distance over time, we can calculate velocity. But of course, computers being computers, division by 0 is somewhat challenging. So we're just going to do a little bit of data munging here to make sure that if we ever have a time delta of 0 or null, we're just going to give it 0 for velocity, but otherwise we'll do the calculation. So if we scroll down to our preview here, look at this. So this is the first entry in the window. And you might think, oh no, we've made a terrible mistake. There's nulls and the velocity is 0. No, because this is the first one in the window, there's no previous entry. So there's no velocity, there's no deltas. That's expected behavior. But if we go down to the next one here, and I'm sorry that my screen is not quite big enough, but we can now see, okay, we've got a T delta and we've got a D delta and now a velocity calculated. Doing just a little bit of sort of mental math here on our T delta. If this is 136988 and this is 136893, it's kind of hard to carry the numbers, but that's approximately 95 for our time delta. And I'm not going to do the square root math in my head, but just sort of looking at it briefly, 27 to 32, 208 to 204. Yeah, D delta of 6.2 looks about right. So we've got our time, we've got our distance, and now we've got velocity. And that's now happening for every single one of these pointer records that are coming in. And the results of this are going to the Moonsense pointer velocity stream. So we've got a stream of data, real time, coming in, constantly calculating the velocities of pointer records as they happen. Any questions so far? Okay, So this is interesting data. What can you do with it? Why do we care? So the next step here is we're going to show off a pipeline that's going to do some summary statistics for us. And it is running. We're getting our sort of 10x multiplied records in, and we've got records coming out. And I'll show the pipeline here. Oops, I'm on the wrong one. Sorry, this is pointer stats. That's the one we want. And this actually is expected. I'll show you why, but this is reflecting back down to less records per second. So our pointer stats, to sort of describe this query a little bit, at a high level, we're taking our Moonsense pointer velocity records. We're making a tumbling window aggregation, and this is just every 10 seconds. And every 10 seconds, we're going to take the time interval and group them by the session ID. So just in 10-second blocks, as we get these records coming in, it's making these windows. And we're going to do some summary stats on it. We're going to count how many records we see. We're going to take the mins, the max, the mean, and then we've got these percentiles. If you need a little refresher on how percentiles work, you can kind of think of the min as the 0th percentile, the max is the 100th percentile, the 50th would be like the median, and then these are sort of the midway points. So between the median and the min would be P25, and between the median and the max would be P75. This gets us sort of a general data distribution for the velocities. We can sort of start to get an idea of what this looks like basically on a graph. And this is, as I understand it, very useful for data scientists to train their models on it. And I realize I should have started running this. So while we are at it, not only are we getting the velocity quantiles, but we can also calculate, what's the total distance traveled, what's the total duration traveled, total velocity. And of course, in this example, I'm only looking at velocity. There's no reason we couldn't be doing the same thing for radius and size and all sorts of other features that data scientists might find useful and could use to sort of train and evaluate their models. This one takes a little bit of time to start up because not only does it set up the new window for you, but it also has to wait the 10 seconds for data. But we do have things coming in. One thing I'm going to do before we sort of look at it, though, is I'm going to start up another data generator with our bot data. And I don't know if we'll quite get it in time, but we might. So here is the results. So every 10 seconds per session ID, we're going to see the summary statistics for the velocity. These are sort of challenging decimal values. So I'm not going to interpret them too broadly, but the output of this could be used now as a sort of a feature set for a data scientist to take. This is our SJ user. There might be one in here for our bot user. I don't know if I caught it in time or not. That's okay. We're not going to wait around for it to preview again. I will assure you that it works. But one of the interesting things is, not being a data scientist, I don't have a full sort of like appreciation or understanding for what algorithms we can run on it. So I'm going to segue into what I'm calling the bad data science aspect of the demo. And let's see if I can find it here. So what I did is, I've got the user data and the bot data being brought in, and it's running through this pipeline. And I just plotted the results. Let me just turn off these lines before there we go. And so all I have here, this top line is describe the axes. These are the quantile values that we saw in our plot below. We have the velocity values here. The interesting thing about this, and again, I'm told by Andre that these are sort of predictive values. This line here is our real user quantiles for velocity. And this line here is our bot user quantiles. So drawing just a couple of lines of best fit here, you can sort of imagine, again, not being a data scientist, these do look different. You could imagine that with these features and potentially other features, a data science team could take these features and start to train a model to basically say, does this user really look like a real user, or is this perhaps coming from a bot? So
yeah. This is great work. Just to intervene very quickly, Josh. In practice, the distinction is not so easily done through just drawing the lines. Yeah. But the underlying signal that the model actually eventually learns to recognize is that network latency and jitter becomes visible in the velocity in a way that's has nothing to do with like a human would actually move their finger on the screen under normal circumstances. And that's basically kind of like how this detector works.
Cool. So that is it. That's pretty much all I have to show. The sort of next steps here, you could imagine creating a connector, an external connector from this data stream out to say S3 or some other data source where a data science team could take this and again, train and evaluate, potentially augment with more features and so on. Yeah, that's pretty much it for today. Are there any questions?
In your example, you showed a tumbling window. Are other types of windowing available, like hopping or session or?
Definitely. I don't know all of the semantics of all of them offhand, so anyone on the call can feel free to correct me, but as I understand it, we have both tumbling, we have tumbling, hopping, and session, and there might even be another kind, but if any other decoders want to step in to correct me, feel free to do so.
Yeah, we have another window, sliding window, but that's basically, a tumbling window. You can use the same syntax for that. Yeah, but in short, we have tumbling window, sliding window, session window. And I think there's another thing. Actually, Flink supports global window. I don't know if we actually would enable that.
Yeah, I think tumbling and sliding are the most common. Tumbling is you move the window the same size increment. So what Josh did here, like every 10 seconds, every 5 seconds. Sliding will let you do things like, I want to look at the last 5 seconds, but I want to move the window every 1 second. I want it to update every 1 second. And then there are some specialized window functions like cumulative windows, which is effectively like a running total. And then there's, I think, an output frequency, if I remember correctly. It's not used commonly. It can be valuable in the case of like, I want to know the total number of records that I have seen over all time, and I want that to be output every 5 seconds or something like that, or the like a running sum or something like that. And then there are like specialized windows around sessions and those kinds of things. So those tend to be more complicated.
Great. And the intermediary like results, the different pipelines, I think you guys call them, those are those stored in like Kafka topics or yeah, where are they stored?
Yeah, so I can take that one. So every time Josh has shown you a stream here under the hood that's actually backed by a Kafka topic and has all the same properties around absorbing back pressure and those kinds of things. So if, for instance, Josh were to stop one of these pipelines, its input will simply accumulate in the preceding stream until he reactivates the pipeline, and then we'll resume and process all of that data. Of course, we have Kafka connectors and those kinds of things. So if you want to have the data be usable by not just decodable pipelines, but by like microservices and like all sorts of other processes like that, or even like online ML systems like Continual or Tecton and like all these other kinds of systems that people like Andre, much smarter than me, know more about than I do, like any of those kinds of systems, then you could simply output the contents of a stream directly to like a Kafka topic that you own and that you control. And I say Kafka, it could also be Kinesis, it could be Red Panda, it could be, soon you'll be able to do Pulsar. So we have that sort of in the works, and not just Kafka, but like Confluent Cloud or, AWS MSK. We don't take a strong position on those kinds of things.
And last question, the connector, I know it was an HTTP endpoint, and so on the source side. And so
That's right.
the Decodable is presenting this endpoint that is collecting the events.
Right.
And then there's
Yeah.
also, is it the same on the kind of the sync as well? You could also send the kind of enriched or transformed events to a downstream endpoint.
Yeah, we have talked about this. We're sort of in the process of exposing the equivalent on the sync. It's a little bit weirder because, and in fact, we're really open to feedback on this. We could do things like post to a REST endpoint that you provide, and then we have to figure out sort of like how authentication works there and like what the payload looks like and those kinds of things. The alternative is we expose another REST endpoint that acts as like that you can long pull, and those would be the two different ways we could do it. I think we're going to do sort of like a webhook sync initially, so that if you have any kind of microservice or something like that that exposes a REST endpoint, we could simply post payloads to you. But be interested in feedback on that to hear exactly what you would like to see out of those, like what the right model is for your applications.
Thank you.
Mm-hmm.
And just to add to that, this mechanism here for like REST data ingest, it's something that Josh right now wrote a script to post the data with, but it's something that we are working towards smoothing out, so that when you go to Moonsense, our webhook mechanism would know about Decodable and the expected REST input formats, and then the wiring the two products together will be trivial.
Josh, so this is brilliant. As a black box, you can see there are like micro batches of device data coming in, and then statistical outputs for training a feature store. But could you give us a little bit of your experience on how did you approach that? I think that for me, looking at what SQL is doing, I would never imagine SQL could do what you've done. But I'm kind of interested how you broke it down into multiple pipelines and just what that process was like.
Sure. I mean, full disclosure, I am not yet a streaming SQL expert either, so it's sort of trial by fire. I think you can really just sort of see it, based here. I mean, being sort of an engineer, you kind of approach things iteratively. Okay, so the first thing we need to do is let's just get the data in and parse it, right? So we know we have this sort of big honking payload here. I was sort of intuitively aware that you want to make sure that we have some time attributes that we can key in on. And also, this nested sort of bundle, that's a lot more keystrokes. I'm a programmer, I'm lazy. So I want to just pull that out. So that was sort of the standard parsing, cleaning stuff that we've sort of done all the time. I guess the next one was maybe a bit of a leap was, I think originally we just thought that filtering the different types of data, telemetry data, into their own streams would be useful. So a payload potentially could come in with, accelerometer data and magnetometer and all sorts of stuff. So I'd originally had pipelines kind of like that extract pointer pipeline that would effectively filter and route and demultiplex those events into individual streams. It seemed like it might be a useful thing to bring them off, potentially join them to other things, do transforms on them. So that was something I'd sort of already had. But as it turns out, sort of given the next use case of determining velocity, that was sort of a kind of a boon for it. Is, in the streaming world, we really do want to have these as individual events, because that opens up a lot of opportunity for these sort of windowed aggregations across events that otherwise wouldn't be possible. And that's sort of seen in this Moonsense velocity calculation. So I will 100% admit I had not used the lag function before really in much of my previous life, or at least in SQL. I've certainly looked at it in other streaming services and Spark and things like that. But just being able to write it out using sort of standard syntax was really quite nice. You can find a million examples of how you're supposed to do this on, not just our documentation, but other folks' documentation. And it just sort of I want to say it's sort of assembled itself. Once you kind of figure out how to do the stateful windowing and peeking back, so to speak, the rest of it's pretty straightforward. You know, it's just sort of math. So that was my general sort of thinking about it. The next step was definitely a bit of a challenge. You know, not the velocity, sorry, the pointer stats, right? So we're doing summary statistics. Some of the stuff, you know, we needed to sort of figure out ourselves and implement and get it working. But you know, at the end of it, we have this sort of pretty rich, you know, feature set being emitted, again, just in pretty standard SQL, which is pretty neat.
I will add here that in my experience in working with streaming system in the past, accomplishing this type of like windowing with exactly once processing, it's insanity. So it's easy to underestimate. I wouldn't underestimate like the immense value created through the state management that Decodable and like the underlying stream processing engine does here, because that's such an important piece of the puzzle.
Yeah, I'd be lying if I said that the exactly one semantics under the hood were a cakewalk. There's a lot of edge cases and rough spots that you need to sort of figure out and you know, sand out. But I think we've done a pretty good job here.
And kind of building on that, could you have combined some of the pipelines into just really much larger SQL queries than you did it for good practice software engineering decomposition?
You know, that's a good question. I suspect that there's some optimizations I could make here. I don't entirely know though, just for the semantics, right? If we're doing this extract pointer, whether it'll let you necessarily embed a cross join on nest into subqueries. I suspect you might be able to just put this all in one sort of scary, you know, SQL clause. That's not the way my brain works. I really do like to have things sort of decomposed. So I'll leave that as an exercise for the reader to determine.
Well, and I hate to bring in data mesh here, but I guess potentially there are some intermediate products that could be useful to feeding other pipelines that don't yet exist.
I think usually that's the core reason that you would sort of disaggregate one query. I mean, there are two reasons we see people do it. One is the pipeline just becomes so complex to sort of think about or to test. It makes sense to shred it into smaller units the way I think Josh has done here. The other is you actually want the intermediate output of, you know, one of these pipelines for like different, you know, use cases or multiple use cases. And in that case, it totally makes sense to disaggregate sort of like this larger, you know, theoretically sort of like single process into multiple steps like that. There can also be operational concerns around sort of like how often do you update the logic on like the sort of cleansing portion versus how often do you update the logic on the analytics portion. And for certain online processes, you might not want to have to disrupt everything every time you want to sort of make a change or something, or test everything, you know, from end to end, you know, so it gives you smaller units to work with. But I think there's lots of different reasons that you would either merge things together or you would split them apart. Merging them together, the only real advantage to that is it's more efficient for the underlying stream processing engine, right? Because you're not actually materializing the result into a stream each time. You know, for decodable, you know, customers, that doesn't matter because that's the part that we take care of. You don't have to worry too much about that. But I think if you are running this on your own hardware, you might care a whole lot about the efficiency of like state management and task allocations and resource management and stuff like that. Luckily, our customers don't have to deal with a lot of that stuff.
Yeah, I like the way that Josh has these individual SQL segments broken up into more manageable chunks. Then once you have these individual pieces, the question becomes how are they interrelated to each other and how they depend and like you were saying, Erica, being able to test and make sure that, individual pipelines or paths through that network are still stable.
Yeah, I think there's a bunch of different sort of common features. We've started to expose some of them. For instance, if you look at any connection in Decodable, we'll tell you which stream it's directly connected to, whether it's the source or the sink and like all these other kinds of things. So like there's a little bit of that connectivity, that lineage information. I think over time, what you will see us do is expose more lineage information to show you like which pipelines are connected to a specific stream. So basically you can walk the graph, the dependency graph of this connection to this stream, to these pipelines, to these streams, to these connections, and be able to follow that through end to end. We do stop you from doing like super dangerous stuff. For instance, like I don't actually think that you can delete a pipeline that's being used, or sorry, delete a stream that's being used by a pipeline and like those kinds of things. So there's some protection in place, to stop you from doing sort of like really, really crazy stuff where you would otherwise lose data. I think larger organizations tend to start to feel that kind of pain. You start getting into like hundreds of engineers that are sort of using streams as kind of APIs between teams or between sort of microservices and stuff. It becomes really, really hard to track impact analysis and sort of like, dependencies and like those kinds of things without sophisticated tooling around that. I think if you ask anybody who has like these large deployments of things like Kafka and Flink and K-streams and stuff like that, they'll tell you stories about somebody deletes a topic and like half the business stops working and like those kinds of things. So it becomes really complicated if you're, if you don't have the right kind of hygiene around it.
Yeah, but even at the smaller scale, like having that lineage information is a good form of like documentation, especially over time as there's turnover within a smaller team.
Yeah, if I had $1 for every time somebody said, what do we use this topic for? Like, what does this do? And like, do we need to keep it? And can I deactivate this pipeline? Just like even questions like that, I think become really, really challenging. Just week to week, unless your memory is better than mine. But I need that kind of help to remember what things do.
So Josh, I think we've also done some work about like resource management outside the UI, right? Like in case you have like tons of pipelines connections you want to manage, would you mind showing us like some of the resource definitions that you had?
Sure. So let me pop over here. Sorry about the Python stack trace. Yeah, there's a lot of work actually going on right now too, even to support, sorry, I've got videos in my screen. I'm just moving it over so I can do things, to support like Terraform, management for, connections, pipeline streams and things like that. So I'll just give you an example. This is our, just a project definition. It's a Git, repo. But we could take a look in here and actually see the YAML that's been actually just generated by the CLI. So if we take a look at, parse, oh, look at that, I've got calc velocity here. So this might not be exactly the same as what I showed, but we can see here, it's a YAML definition. You've got IDs, name, description, and the SQL. I think it looks pretty close. And it, target state. So effectively you could manage state using YAML definitions, change them here, commit them, and then, in the sort of fullness of time, do, like a Terraform apply and have it update the state for you. And that exists, not just for pipelines, so we go into connections, it's the same sort of thing. Here's a REST connection defined, it's got the schema. You can see the really sort of intricate bundle schema here. But yeah, and here's our properties. So everything that is sort of a part of a connection is exposed as YAML, and not just YAML, you can get it back as JSON and regular sort of command line. But again, if you're thinking in the scheme of sort of state management, having code as configuration, this is definitely sort of the direction we're trying to head with that.
It's very cool. So there's a lot to digest there, but it's great work. Does anybody have any other questions before we close out here? If not, say, Andre and team, thank you, and Josh, thank you for that tour de force on SQL. You may say you're not an expert. You're my expert.
Thank you very much.
And so this was a kind of informal demo. It didn't seem very informal to me, but we'll be coming back next month with a webinar where we'll hopefully run through the scenario with a real device, Andre, do you think? And show some of the stuff running, maybe with a few pictures of the pipelines talking to each other. Yeah. So watch out for that. That webinar will be ready for registering in a couple of days. And again, thanks everybody. And Andre, Josh, thank you so much. That was great.
Thank you.
Thank you.
Take care.
Thank you.